6.3 Futures. Async.io's future objects look and behave pretty much like concurrent.future's future objects, but they're not interchangeable. They have subtle differences in behavior, and of course major differences in how they interact with the underlying system, which are completely different. And of course major differences in how they interact with the underlying systems, which are completely different. Still, each feature is a way of referencing a value that may or may not have been computed yet, and if necessary a way of waiting for that value to become available. We're going to take a look at how the async.io.future object is most often used, or several ways in which they are commonly used. And we're going to also study for a moment why iterators can be a trouble with async.io, and how the futures can help to solve that problem. We're also going to take a look at when we should be using coroutines and when it's sufficient to simply use a future. The most commonly used feature of a future is to wait for its value to be determined and then retrieve the value. For async.io's future objects, this is done simply by yielding from the future. That will tell the scheduler to pause the coroutine until the value of this future becomes available, after which the future value is sent into the coroutine as the result of the yield from expression. If the future represents a raised exception instead of a value, that exception is re-raised from the yield from expression. If we don't want to wait, we can call the done method to check whether a future is ready, and if it is, we can call the result method to retrieve the value. So the syntax and semantics are a little different, but the basic idea of a future is the same in async.io and concurrent.futures. When we're working with async.io, we use future objects all the time in all the same places that we might in concurrent.futures. But there's one particularly important case where we use features that's unique to async.io. To understand it, we need to take another look at how async.io's coroutines are built. Specifically, we need to remember that async.io's coroutines are a special case of Python's generator objects, which are meant to interact with the scheduler, rather than the normal looping functions. They certainly don't work properly when a for loop tries to iterate over them, and any generator that will work in a for loop won't work as a coroutine. Iteration is a big deal in Python, so how do we deal with situations where we want to, for example, iterate over values that were retrieved from across the network? The answer is that we write a normal generator to interact with the loop mechanisms, but instead of having it produce the real values we're iterating over, it produces futures. Meanwhile, one or more other tasks are busy filling in values for those futures, happily running coroutines under the direction of the scheduler. On the other side of the iteration, and back under direct control of the scheduler, we yield from the futures, retrieving the actual values as they become available. The scheduler's task objects are much more lightweight than operating system processes, but future objects are even slimmer. In the example we just saw, a new task was launched to calculate the value for each of the futures we yielded, but in a lot of cases it would be more efficient to modify the code so that there's just one task working on all of the futures. That only makes the code a little more complicated, as we see here, and it makes the overhead much smaller. This sort of paradigm can be made simpler still by using queue objects, as we'll see in the next video. Also, take note that even though the iter function uses yield from, it's not a coroutine. It's using that expression in a more standard yield from the values of this iterable sense. In the last two examples, we assumed a fixed and already known number of objects to be iterated over. When we don't know how many objects will be iterated over when iter is called, things get more complicated, because how many features should we create to represent an unknown number of values? Well, in this example, we've made the body of the iter function into a while loop, generating one feature each time through the loop and handing off the decision on when the iterator should stop looping to the fill coroutine. This pattern too can be written better using async.io's queue class instead of the list we're using here, but we're going to get to that in a little while, so it's not involved in this example. We have to be careful of doing things this way because even though it works fine for for loops that yield from the future one at a time, it goes very wrong when we try the iteration without occasionally yielding to the scheduler. Passing an instance of this version of the slow sequence into a list function, a constructor for example, will freeze and then crash the program, as Python tries to make an infinitely long list. That's because the filler will never be done, because the list function keeps asking for more values without giving the scheduler any opportunity to run. Depending on usage patterns, it's also possible to have features at the tail end of the iteration that never receive a value thanks to having been yielded by the iterator just before the filler decided it was done. That's not as big a problem as a freeze crash, but it's something to keep an eye on. There are ways to design around these problems too. For example, we could have the iterator produce features of fixed-size chunks of values, and check between chunks whether another chunk is available yet. Alternately, we could have the filler run ahead as fast as it can and have the iterator just loop over the items already loaded, with the understanding that iterating over the object again might later produce different objects. No doubt you can think of other options as well. There's no best practice in this case. We should just pick a paradigm that works for our program. So, futures are rather a lot the same in terms of functionality and their basic paradigm between concurrent.futures and async.io. Async.io allows us to simply yield from a future, to wait for its value to become available and to retrieve it. Apart from that, it behaves and looks very much like a concurrent.futures future. Coroutines are generators, so the iteration protocol can interfere with async.io's task scheduling. But we can avoid that problem by using as the thing to iterate over rather than the objects themselves. Futures have extremely low resource requirements. So, when we have a choice between writing a function that returns a future or writing a coroutine, it's better to choose a function that returns a future. However, there are times when a coroutine is necessary because it actually needs to do processing, and in those cases, we should not hesitate to use the coroutine. In the next video, we're going to look at the aforementioned queue class, along with other ways of synchronizing and communicating between tasks.